Look up at the night sky. Every star you see, every distant galaxy, every shimmer of cosmic light, it's all part of something so vast, so ancient, it's almost impossible to truly grasp. But here's what might truly bend your mind. The universe isn't just big, it's growing, stretching, expanding in every direction, carrying galaxies away from each other in a silent, relentless tide. And the rate at which it's doing this, the speed of this cosmic expansion, is one of the greatest scientific mysteries of our time. You might think measuring how fast the universe expands would be straightforward. After all, astronomers have some of the most advanced tools ever created. But the reality is, this simple question has sparked one of the most heated debates in modern astronomy. Two completely different methods of measuring this expansion rate, the Hubble constant, keep giving us two different answers. They don't match, they should match. And this discrepancy has created what scientists call the Hubble tension, a puzzle so profound it threatens to reshape our understanding of the cosmos itself. So what's really going on? Is it an error in our measurements, or could it be that our entire model of the universe is missing something fundamental? In this video, we're going to explore 30 astonishing facts about the expansion rate of the universe, from how we first discovered it was expanding at all, to why this cosmic speed limit has astronomers so deeply divided. We'll journey through space and time, uncovering clues that challenge not only what we know, but how we know it. This isn't just a story about numbers. It's a story about our place in the cosmos and the thrilling, humbling pursuit of truth in a universe that keeps surprising us. Before 1929, the prevailing scientific belief was that the universe was static, eternal, and unchanging in size. This was the cosmos Einstein himself had described, a grand but essentially motionless stage. Then along came an astronomer named Edwin Hubble, working with a powerful new telescope atop Mount Wilson in California. By meticulously observing a class of stars known as Cepheid variables in what were then called spiral nebulae, Hubble made two monumental realizations. First, he confirmed that these fuzzy patches of light were not part of our own Milky Way, but were in fact entire other galaxies, island universes stretching far into the void. This alone redefined our cosmic address, moving us from a single galaxy to a universe teeming with them. But his second discovery was even more profound. By carefully measuring the light from these distant galaxies, Hubble noticed something strange and utterly revolutionary. The light from nearly all of them was shifted toward the red end of the spectrum. This redshift wasn't just a curiosity, it was a cosmic speedometer. Just as the pitch of a siren drops as an ambulance races away from you, this redshift indicated that these galaxies were all speeding away from us. And the most staggering part, the farther away a galaxy was, the greater its redshift, and therefore the faster it was receding. This relationship, now enshrined as Hubble's law, painted a clear and shocking picture. The very fabric of space itself is stretching, carrying galaxies along with it like raisins in a rising loaf of bread. The universe wasn't static at all. It was dynamic, evolving, and expanding in every direction. This single observation shattered humanity's conception of a steady-state cosmos and laid the foundation for the entire story of the Big Bang. This discovery of an expanding universe leads us to a critical point that is often misunderstood. When we say galaxies are moving away from us, it's not because they are hurtling through space like rockets flying away from an explosion. The reality is far stranger. The galaxies themselves are, for the most part, relatively stationary within the fabric of the cosmos. What's actually happening is that the very fabric of space itself, the empty void between all matter, is stretching and growing. Think of it not as objects moving through a container, but the container itself getting larger. The most famous and effective way to picture this is the raisin bread analogy. Imagine you have a lump of dough with raisins scattered throughout it. This dough represents the fabric of space, and each raisin is a galaxy. Now, as you bake the bread, the dough rises and expands uniformly in all directions. What happens to the raisins? From the perspective of any single raisin, all the other raisins are moving away. A raisin that was originally 1 inch away is now 2 inches away. A raisin that was 2 inches away is now 4 inches away. The farther away a raisin is, the faster it appears to be receding, not because it's moving through the dough faster, but because there is simply more expanding dough between you and it. This distinction is absolutely crucial. If galaxies were just flying through static space, the universe would have a center, a point from which the Big Bang originated that everything is flying away from. But the raisin bread model shows us there is no center. Every single raisin, every single galaxy, sees all the others moving away from it. We are not in a special or privileged location. The view from any point in the universe would be the same. The expansion is a property of space itself, a fundamental feature of our universe that means the distance between any 2 points that are not gravitationally bound, like galaxies in different clusters, is continuously increasing. This underlying mechanism is what Edwin Hubble's observations revealed, and it remains the cornerstone of our modern cosmological model. So how do we actually put a number on this expansion? This is where the Hubble constant comes in, a single, crucial number that quantifies the speed of the universe's growth. Designated by the symbol h0 or h0, this constant is the key to measuring our cosmic expansion rate. Its unit of measurement might sound complex at first, kilometers per second per megaparsec, but it unravels a beautifully simple concept. Let's break that down. A megaparsec is an astronomical unit of distance, a truly staggering one. 1 parsec is about 3.26 light years, and a megaparsec is 1,000,000 of those. So we're talking about an immense scale. Now, the Hubble constant tells us that for every megaparsec of distance between 2 galaxies, the space between them is expanding, causing them to recede from each other at a certain speed, measured in kilometers per second. For example, if the Hubble constant were measured to be 70 kilometers per second per megaparsec, it would mean a galaxy located 1 megaparsec away from us is moving away at 70 kilometers per second. A galaxy 2 megaparsecs away would be receding at 140 kilometers per second, and a galaxy 10 megaparsecs away would be speeding away at 700 kilometers per second. It's a linear relationship, double the distance, double the apparent recession velocity. This single number, the Hubble constant, is arguably one of the most important in all of cosmology. It's not just a speed limit sign for the universe. It's a fundamental parameter that allows us to estimate the age of the universe, to understand the nature of dark energy, and to trace the entire cosmic history back to the Big Bang. Pinpointing its exact value with precision has become one of the grandest challenges in modern science. For decades, astronomers have worked tirelessly to measure the Hubble constant with ever greater precision, expecting that with better technology would come a single, agreed-upon answer. Instead, they've walked directly into a cosmic crisis. The field is now split by 2 brilliant, yet seemingly incompatible, methods for measuring the expansion rate, and they stubbornly refuse to agree. This isn't a minor discrepancy, it's a fundamental clash of results that has become the most significant puzzle in modern cosmology. On one side of this divide is a technique often called the distance ladder. This is a direct, step-by-step method that builds a chain of measurements out into the cosmos, much like an astronomer's version of a tape measure. It starts right here in our cosmic neighborhood by using geometry to pin down the distances to nearby stars with incredible accuracy, a method known as parallax. These well-understood stars, specifically a type called Cepheid variables, have a unique property. Their intrinsic brightness is directly tied to their pulse rate. By measuring how fast they pulsate, astronomers can determine their true brightness. Then, by comparing that known true brightness to how dim they appear from Earth, they can calculate a precise distance. These Cepheids act as the first crucial rung on the ladder. We then use these calibrated Cepheids to find and measure the distance to galaxies that contain both Cepheids and another, even brighter type of cosmic milepost, a specific kind of stellar explosion known as a Type 1a supernova. These supernovae are so brilliantly consistent they're called standard candles. Once we know the true distance to these supernovae in a few galaxies, we can spot them in galaxies billions of light years away. By measuring the redshift of these incredibly distant supernovae and knowing their distance from the standard candle property, we can directly calculate the Hubble constant. This meticulous cosmic ladder building, championed by teams like the one led by Nobel laureate Adam Rees, consistently yields a value around 73 kilometers per second per megaparsec. On the other side of the debate, we have a method that takes a completely different approach. Instead of building a ladder to the present-day universe, it uses the afterglow of the Big Bang itself, the cosmic microwave background, or CMB, as a pristine snapshot of the infant universe. The CMB is a faint radiation field that fills all of space, a cold relic from when the universe was just 380,000 years old. By mapping the tiny fluctuations in this background radiation with exquisite detail, as missions like the Planck satellite have done, cosmologists can deduce the universe's fundamental ingredients, the amounts of normal matter, dark matter, and dark energy. Using our extremely well-tested model of cosmic evolution, known as the Lambda-CDM model, they can then fast-forward this model 13.8 billion years to predict what the Hubble constant should be today. This method doesn't measure the current expansion directly. It predicts it based on the early universe's conditions, and this prediction gives a value of around 67 kilometers per second per megaparsec. The difference between 73 and 67 might seem small, but in the realm of cosmology, where measurements are now incredibly precise, this gap is a chasm. The error bars on these measurements, the range of uncertainty, no longer overlap. This means the probability that this difference is just a fluke is astronomically small. We are left with two impeccably crafted, independently verified results that simply cannot both be correct under our current understanding of physics. This persistent and growing disagreement is what scientists have dramatically named the Hubble tension. It's not just a minor calibration issue, it's a direct challenge to our standard model of the universe, suggesting that something in our cosmic recipe, perhaps a completely unknown form of energy or a flaw in our theory of gravity, is missing. To truly grasp how we measure the expansion of the universe directly, we need to understand the tool at the heart of the distance ladder method, the standard candle. In astronomy, a standard candle is any object whose intrinsic or true brightness is known. This is a powerful concept because light obeys a simple, unwavering rule. It dims with distance in a perfectly predictable way. Imagine you have two identical light bulbs. If one is 10 feet away and the other is 100 feet away, the more distant one will appear significantly dimmer. If you know both bulbs are identical, that they both output the same amount of light, you can use how dim the far one appears to calculate exactly how far away it is. Astronomers apply this same principle to celestial objects, but the challenge is finding those reliable, identical cosmic light bulbs across the vastness of space. The first and most crucial rung on the cosmic distance ladder is built using a special class of stars known as Cepheid variables. These stars are not constant, they rhythmically pulsate, growing brighter and dimmer over a regular period. In the early 20th century, astronomer Henrietta Swan Leavitt made a groundbreaking discovery while studying these stars in the Magellanic Clouds. She found that the period of a Cepheid's pulsation, the time it takes to go from bright to dim and back again, is directly proportional to its true luminosity. A Cepheid that pulses slowly with a long period is inherently very bright. One that pulses quickly with a short period is inherently dim. This period-luminosity relationship was a master key for astronomy. By simply measuring the pulse rate of a Cepheid variable, astronomers can immediately know its true brightness. Then, by measuring how faint it appears from Earth, they can calculate its distance with remarkable precision. These stars become our first reliable milestones in the local universe, but Cepheids, as bright as they are, have their limits. We can only see them in relatively nearby galaxies. To reach across billions of light years, we need a far brighter beacon. This is where the universe provides a spectacular solution: Type 1, a supernova. These are colossal explosions that mark the violent death of a certain kind of star, and they are arguably the most perfect standard candles in cosmology. What makes them so valuable is their consistency. Every single Type 1, a supernova, is thought to originate from a white dwarf star that accretes matter from a companion until it reaches a very specific critical mass. This triggers a thermonuclear explosion that is almost identical every time. Because the explosion physics is so uniform, these supernovae all peak at almost exactly the same incredible intrinsic brightness, outshining entire galaxies for a brief period. Their phenomenal and consistent brilliance makes them visible from halfway across the observable universe. Now, the construction of the distance ladder begins. Astronomers first use the trusty method of parallax, observing how a star's position shifts against the background when viewed from different points in Earth's orbit, to get direct geometric distances to the very closest Cepheid variables. This calibrates the first step. Next, they find galaxies that contain both these well-understood Cepheids and a Type 1, a supernova that has occurred at some point. Since the Cepheids give a precise distance to that galaxy, astronomers can then look at the peak brightness of the supernova that happened there. They know how bright it should have been, and they measure how dim it appeared. This precisely calibrates the true power of a Type 1, a supernova, turning it into a perfectly known standard candle. This is the critical link that connects the nearby universe to the far distant cosmos. With this link established, the final step is to measure the expansion rate. Astronomers now search for Type 1, a supernova exploding in galaxies billions of light years away. Because these supernovae are now calibrated standard candles, their observed dimness directly reveals their vast distance. At the same time, they measure the redshift of the host galaxy's light, which tells them how much the universe has stretched and how fast the galaxy is receding. By collecting data from many such distant supernovae, they can plot a graph recession velocity against distance. The slope of the line that fits this data is the Hubble constant itself. This meticulous step-by-step process, climbing from parallax to Cepheids to supernova, gives us our most direct measurement of how fast the cosmos is growing today. While the distance ladder method peers into the relatively recent cosmic past to measure expansion directly, the other side of the great debate takes us back to the very beginning, to a time before stars or galaxies even existed. To understand this completely different approach, we need to talk about the oldest light in the universe, the cosmic microwave background, or CMB. This faint glow is the cooled remnant of the hot, dense fireball of the Big Bang, a snapshot of the cosmos when it was a mere 380,000 years old. For 13.8 billion years, this light has been traveling across the expanding universe, and it now permeates all of space, a cold whisper of our creation. It was first accidentally discovered in 1964 by Arno Penzias and Robert Wilson, who initially mistook the persistent hiss in their radio antenna for interference from pigeon droppings. This universal background radiation is incredibly uniform, but not perfectly so. Embedded within it are tiny, faint variations in temperature, tiny bumps, and dips no larger than 1 part in 100,000. These anisotropies are not random noise. They are the cosmic seeds from which the entire large-scale structure of the universe would eventually grow. The slightly denser regions, imprinted as slightly warmer spots in the CMB, are the gravitational wells that would, over billions of years, pull in enough matter to form galaxy clusters and the vast cosmic web we see today. To read this ancient cosmic blueprint, we needed a telescope of extraordinary sensitivity, one that could map these minute fluctuations with precision from beyond the interfering blanket of our atmosphere. This was the monumental task of the Planck spacecraft, a European Space Agency mission that operated from 2009 to 2013. Positioned at a stable gravitational point in space called L2, far from Earth's heat and radio noise, Planck's instruments scanned the entire sky not once, but multiple times, measuring the temperature of the CMB with a sensitivity down to a few millionths of a degree. The final map it produced is arguably one of the most important in all of science, a detailed, all-sky picture of the infant universe, a cosmic fossil preserved in microwaves. But how does this detailed baby picture of the universe tell us how fast it's expanding today? The key lies in the precise pattern of those hot and cold spots. The sizes of these fluctuations are not arbitrary. They are governed by the physics of sound waves oscillating in the primordial plasma of the early universe. The most common or preferred size of these waves acts as a standard ruler etched across the sky. We know its absolute physical size from our understanding of fundamental physics. By then measuring how big this ruler appears to be on the sky, its angular size, cosmologists can perform a simple geometric calculation to determine the distance to the CMB, and thus the scale of the universe at that very early time. This measurement is exquisitely sensitive to the contents of the universe, the amounts of normal matter, dark matter, and dark energy, because each of these components affects how the universe has expanded from that early moment until now. By feeding the precise statistics of the CMB's patterns into our extremely successful standard model of cosmology, known as lambda cold dark matter, scientists can effectively win the cosmic clock forward. The model uses the initial conditions from Planck's snapshot to simulate the entire evolution of the universe, predicting with great confidence what the expansion rate should be in the present day. This method doesn't directly measure today's expansion, it infers it through the power of our physical models. And this inference, based on the pristine conditions of the infant universe, gives us a Hubble constant value of around 67 kilometers per second per megaparsec, a figure that stands in quiet, confident, and deeply puzzling contradiction to the one we get from looking at the stars. At first, many in the scientific community assumed the growing disagreement between the distance ladder and the CMB measurements was simply a case of improving technology. The thinking was that as our instruments became more sensitive and our methods more refined, the error bars, the range of uncertainty around each measurement, would inevitably shrink until they finally overlapped, revealing a single, unified value for the Hubble constant. This is how science typically progresses, with better data resolving old arguments, but in this case, something deeply counterintuitive has happened. Instead of converging toward a consensus, the two methods have steadfastly refused to meet. With every new satellite launch, every more powerful telescope, and every more sophisticated analysis, the gap hasn't narrowed. It has, in fact, become more pronounced and more statistically significant. The early results from the Hubble Space Telescope hinted at a problem. The exquisite data from the Planck satellite solidified it. And now, newer observations from instruments like the James Webb Space Telescope, which was specifically designed to cross-check the Hubble measurements by observing Cepheids with unprecedented clarity, have only served to reinforce the original distance ladder value, further cementing the divide. The error bars on both sides have shrunk dramatically, which is a testament to our incredible technical skill, but they have shrunk away from each other like two strands of a rope being pulled taut. This isn't a case of sloppy measurements, it's a case of two impeccably careful and precise experiments, operating on entirely different principles, yielding two undeniably different answers. The probability that this disagreement is merely a fluke, a statistical accident, has now dwindled to less than 1 in a million. This is what transforms the situation from a curious inconsistency into a full-blown crisis in cosmology. It strongly suggests that we are not dealing with a correctable error in our observations. The persistent and growing tension points toward something far more exciting and profound, a fundamental flaw or an incomplete piece in our otherwise incredibly successful standard model of the universe. We are likely staring at the first tantalizing evidence of new physics, a cosmic clue that our understanding of the fundamental forces, the nature of dark energy, or the fabric of spacetime itself requires a revolutionary update. For most of the 20th century, astronomers working with the legacy of Edwin Hubble operated under a single, reasonable assumption that the expansion of the universe must be slowing down. It seemed like simple logic. The entire cosmos is filled with matter, and matter exerts gravity. Gravity is an attractive force pulling things together. So even though the initial impulse of the Big Bang sent everything flying apart, the collective gravitational pull of all the galaxies, gas, and dark matter should have been acting like a cosmic brake, relentlessly tugging on the fabric of space, gradually slowing the rate of expansion over billions of years. The biggest question in cosmology was simply how much it was slowing down. Would there be enough matter to eventually halt the expansion and pull everything back together in a big crunch? Or would the universe just keep expanding forever, slowing to a near stop but never quite reversing? This was the central debate. Then, in 1998, 2 independent teams of researchers made a discovery so shocking, so counterintuitive, that it turned all of cosmology on its head and netted them the Nobel Prize. They weren't measuring a slowdown, they were measuring a speed up. The expansion of the universe wasn't decelerating at all. It was accelerating. The teams, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Rees, were using the same powerful tool we just discussed, distant Type 1, a supernova. Their goal was to measure the deceleration parameter by observing how the expansion rate had changed over cosmic time. They reasoned that if the universe was slowing down, then the expansion must have been faster in the past. To see this, they needed to look far back in time, which in astronomy means looking far out into space. They searched for supernovae in extremely distant galaxies, billions of light years away. The light from these explosions had been traveling for most of the age of the universe, so they were effectively seeing the expansion rate as it was billions of years ago. They would then compare this ancient rate to the expansion rate in the more recent, closer universe. They expected to see that the more distant supernova, representing the younger universe, were receding faster than the standard Hubble law predicted, evidence that the expansion has since slowed. Instead, they found the exact opposite. The incredibly distant supernova were significantly dimmer than they should have been if the expansion had been continuous at today's rate. This extra dimness meant these supernovae were even farther away than anyone had calculated. The only possible explanation was that in the past, the universe was actually expanding more slowly than it is today. Billions of years ago, the cosmic brakes were applied more firmly, and since then, someone or something has been pressing down on the accelerator. This discovery was so utterly unexpected that the teams spent years double-checking, triple-checking, and searching for every possible alternative explanation. Could it be cosmic dust dimming the light? The data said no. Could it be that the supernova were inherently different in the past? All the evidence pointed to them being the same brilliant standard candles. There was no avoiding the conclusion. Some mysterious, repulsive force must be at work, counteracting the pull of gravity and pushing galaxies apart with ever-increasing force. This unknown component was christened dark energy. We cannot see it, we cannot detect it directly, but we can see its profound effect on the dynamics of the entire cosmos. It is as if empty space itself possesses a latent energy that causes it to expand at an accelerating rate. This revelation completely redefined our cosmic inventory. We now understand that the universe is primarily composed of things we cannot see. About 68% dark energy, 27% dark matter, and a mere 5% the normal atoms that make up everything we know, stars, planets, and us. The fate of the universe is no longer a question of a big crunch or a gradual slowdown. If dark energy continues to dominate, the expansion will accelerate forever, eventually leading to a cold, dark, and isolated end where galaxies beyond our own local group fade over the cosmological horizon, their light never able to reach us again. The discovery of this acceleration didn't just solve an old problem. It unveiled a far deeper and more profound mystery about the fundamental nature of reality. Given its monumental importance, you might assume the Hubble constant is, as its name implies, unchanging. But here's a cosmic curveball. The Hubble constant is not actually constant. It's a measure of the expansion rate right now, but that rate has changed dramatically over the 14 billion-year history of the universe and will continue to evolve far into the future. The story of this changing expansion is a gripping tug of war between two titanic forces, the relentless pull of gravity and the mysterious, repulsive push of dark energy. To understand this cosmic battle, we need to rewind time all the way back to the Big Bang. In the very first instant, the universe underwent a period of incomprehensibly rapid expansion known as inflation, where space itself expanded faster than the speed of light. After this initial burst, the expansion settled into a more predictable rhythm, but it was still dominated by the dense, pervasive presence of matter and radiation. For the first several billion years, gravity was firmly in control. Imagine rolling a ball up a very steep hill. The initial explosive energy of the Big Bang sent the ball flying upward, but gravity immediately began pulling back, slowing its ascent. This is the decelerating universe astronomers expected to find before the shocking discovery of dark energy. Every galaxy attracted every other galaxy. The collective mass of all the normal matter and the invisible dark matter acted as a cosmic brake, tirelessly working to slow the expansion down. If this were the entire story, the expansion would have continued to decelerate forever. But around 5 billion years ago, something remarkable happened. The universe had expanded so much that the density of matter, which dilutes as space grows, became sufficiently thin. Meanwhile, the density of dark energy, which appears to be an intrinsic property of space itself, remained constant. As the universe grew, there was literally more space and therefore more dark energy. Think of it like this: matter's influence fades as the cosmos expands, but dark energy's influence grows stronger because there's more of it pushing things apart. 5 billion years ago, the scales finally tipped. The repulsive force of dark energy overcame the attractive force of gravity, and the universe transitioned from braking to accelerating. It was as if our ball, still rolling up that hill, suddenly encountered a downward slope and began rolling faster and faster without any extra effort. The Hubble constant at that moment began to increase. The present-day value we are trying so hard to measure is just a single day to point on this grand curve of cosmic acceleration. This profound shift in dominance dictates the ultimate fate of everything. If dark energy continues to behave as our current models suggest, its influence will only strengthen. The acceleration will become more and more violent, eventually tearing apart all structures that are not bound by exceptionally strong gravity. First, the connections between galaxy clusters will vanish as they accelerate beyond each other's observable horizons. Billions of years later, the gravitational grasp of individual galaxies will be overcome, and even stars within a galaxy will be pulled apart. In a terrifyingly distant future, the accelerating expansion could become so powerful that it overwhelms the very forces holding atoms together, leading to a hypothetical end of the universe known as the Big Rip. The Hubble constant is not a fixed speed limit sign. It is the reading on a cosmic accelerometer that is constantly changing, telling a story of a universe caught in an epic struggle between creation and dissolution. This acceleration driven by dark energy isn't just a curious fact about the cosmos. It hints at a potentially violent and ultimate fate for the universe itself, a theoretical endgame so extreme it makes the heat death of the universe seem almost peaceful. This scenario is known as the Big Rip, and it stands as one of the most dramatic and unsettling possibilities on cosmology's long-term forecast. The entire concept hinges on the specific nature of dark energy. Our current best model describes it using a parameter called the equation of state, symbolized as W, for the cosmological constant that Einstein initially proposed, a form of energy with constant density. This value is exactly -1. In this model, dark energy's repulsive force is stable, leading to an eternal, ever faster expansion that isolates galaxy clusters but doesn't immediately destroy them. But what if dark energy isn't constant? What if its strength actually increases over time? This is where the physics becomes terrifying. If the parameter W is less than -1, meaning the dark energy equation of state is more negative than -1, we enter the realm of what physicists call phantom dark energy. This isn't just a repulsive force, it's a force that grows stronger as the universe expands, becoming more potent and more destructive the more it succeeds in stretching the fabric of space. To grasp how phantom energy could lead to a big rip, we need to consider the fundamental forces that hold everything together. Our reality is built on a hierarchy of bonds, from the unimaginably strong to the relatively weak. At the largest scale, the gravitational glue of galaxy clusters is the easiest to overcome. The expansion of the universe is already pulling many of them apart. On a smaller scale, the gravity binding individual galaxies like our Milky Way is stronger, and the expansion hasn't yet overcome it. Smaller still, our solar system is held fast by the sun's gravity. Our planet is bound by its own gravity, and you and I are held together by the electromagnetic force, the chemical bonds that keep our molecules intact. The strongest force of all, the nuclear force, holds the very protons and neutrons in the nuclei of our atoms together. The Big Rip scenario asks a simple, horrifying question. What if the accelerating expansion doesn't stop at merely separating galaxies? If phantom dark energy exists and its repulsive power grows without limit, there would come a finite time in the future when the expansion rate of the universe becomes infinite. This isn't just fast, it's a fundamental breakdown of physics where the scale factor of the universe hurtles toward infinity in a finite amount of time. In this final moment, the expansion would no longer be a gentle stretching of space between distant objects. It would become a violent, disruptive force that overwhelms every single bond in existence, no matter how strong. The end would not come from the outside in, but from the largest scales down to the very smallest. First, the weakening gravitational bonds holding galaxy clusters together would finally snap, flinging them into an ever-widening emptiness. Not long after, the gravity binding individual galaxies would be overcome, and galaxies themselves would be shredded, their stars scattered into the void. Then the expansion would tear into solar systems. The sun's gravitational hold on Earth would be broken. As the end draws near, the force would target the planets and stars themselves, ripping them apart against their own gravity. In the last terrifying minutes, the expansion would overwhelm the electromagnetic forces holding our bodies and our planet together, dissolving everything into a thin, expanding cloud of unbound particles. And in the final fraction of a second, the unimaginable would happen. The expansion would exceed the strength of the nuclear strong force, tearing apart atomic nuclei themselves. The universe would culminate not with a whimper, but with a scream, as every single atom, every fundamental particle, is pushed so far apart that no future interaction is ever possible. The cosmos would become a cold, utterly empty and lifeless void, where the concept of distance has lost all meaning because there is nothing left to measure between. The timing of this potential apocalypse, should the phantom energy hypothesis be correct, is calculated from the current observed expansion rate and the hypothesized value of W. Current observations still comfortably place W at or very near -1, favoring the more gradual, though still bleak, heat death scenario. But if future measurements ever conclusively show W to be less than -1, we could, in theory, calculate a doomsday date. Based on some models, if phantom energy is real, the Big Rip could occur in as little as 22 billion years from now. While that is an almost incomprehensibly long time away, far longer than the current age of the universe, it is still a finite timeline for a definitive and absolute end. The Big Rip remains a speculative possibility, but it is a powerful reminder that the nature of dark energy is the central question in cosmology. Its properties don't just dictate how fast the universe is expanding today, they hold the key to the ultimate fate of every single thing that exists. It's humbling to realize that the very discovery of the expanding universe began with a measurement that was spectacularly wrong. When Edwin Hubble first published his landmark paper in 1929, he announced a value for the expansion rate that would make any modern cosmologist gasp. His initial calculations suggested the universe was expanding at a breakneck speed of approximately 500 kilometers per second per megaparsec. To put that in perspective, if that number were correct, a galaxy 1 megaparsec away would be shooting away from us at 500 kilometers per second. A galaxy 10 megaparsecs away would be receding at a staggering 5,000 kilometers per second. This value implied a cosmos that was not only expanding, but doing so at such a ferocious pace that it would have been incredibly young, less than 2 billion years old. This immediately created a glaring contradiction, as geologists already had evidence that the Earth itself was older than that. The universe simply couldn't be younger than the planet it contained. So how did one of the greatest astronomers in history get it so dramatically wrong? The answer lies not in a failure of intellect, but in the immense challenges of cosmic distance measurement and the limited tools of the time. Hubble's monumental work relied on the same fundamental method we use today, identifying Cepheid variable stars in distant galaxies and using their pulsation period to determine their true brightness. However, he was working with a critical misunderstanding. Hubble, along with everyone else at the time, was conflating two distinct types of Cepheid variables. What he didn't know was that Cepheids come in different populations. The classic, well-understood Cepheids are population 1 stars, which are younger, metal-rich, and found in the galactic disk. But there is another class, population 2 Cepheids, which are older, metal-poor, and often found in globular clusters. Crucially, these two types have different period luminosity relationships. A population 2 Cepheid with the same pulse period as a population 1 Cepheid is actually intrinsically fainter. This distinction was the source of the error. Many of the stars Hubble identified as standard candles in distant galaxies were likely the fainter population 2 variety, because he assumed they were as bright as the population 1 Cepheids he had calibrated locally. He calculated that they were much closer than they truly were. If a star is actually fainter than you think, but it appears a certain brightness in your telescope, you will wrongly conclude it is much nearer to you. By underestimating the true distances to these galaxies, Hubble consequently underestimated the scale of the universe. When he then plotted these underestimated distances against their recession velocities, the slope of the line, the Hubble constant appeared incredibly steep. The galaxies seemed to be flying away at tremendous speeds because he thought they were much closer than they actually were. It was a classic case of a calibration error at the very first step of the cosmic distance ladder, and it reverberated through every calculation that followed. The process of correcting this error became the story of 20th century cosmology itself. Astronomers like Walter Baade played a pivotal role. During blackout conditions in World War II Los Angeles, Baade used the Mount Wilson telescope under gloriously dark skies and made a crucial discovery. He was able to resolve individual stars in the Andromeda Galaxy's central region, and realized they were a different, older population than the stars in the spiral arms. This led him to define the two stellar populations and, crucially, to recognize the dual nature of Cepheid variables. He recalculated the distance to Andromeda, effectively doubling it. This correction alone instantly doubled the size of the known universe and halved Hubble's original constant. Later, another astronomer named Alan Sandage, who was essentially Hubble's successor, continued to refine these measurements. He accounted for other factors, like the fact that what Hubble thought was a single bright star in a galaxy was often actually a cluster of stars or a luminous gas cloud. Each correction pushed the true distances farther out and, in turn, reduced the estimated expansion rate. Through decades of painstaking work, the value steadily dropped from 500 to 250 to 100 and finally down to the range we debate today. Hubble's original miscalculation by a factor of 7 is not a mark of failure, but a powerful testament to the scientific process. It shows how our understanding of the cosmos is built incrementally through careful observation, the correction of errors, and the relentless pursuit of precision, transforming a profound initial discovery into an ever sharper picture of our expanding universe. This profound connection between the expansion rate and the age of the cosmos is one of the most elegant and consequential relationships in all of cosmology. It's a direct and inverse link. The faster the universe is expanding today, the less time it could have taken to reach its current size, and therefore the younger it must be. Conversely, a slower present-day expansion rate suggests a more leisurely, drawn-out cosmic journey pointing toward an older universe. Think of it like a simple car trip. If you're driving at a constant 100 kilometers per hour and you've covered a distance of 100 kilometers, it's easy to calculate that you've been driving for exactly 1 hour. Now, if you were somehow told that you had actually been driving for 2 hours, you would instantly know your average speed must have been slower, only 50 kilometers per hour, to cover the same distance in that longer time. The distance traveled, your speed, and the time elapsed are all inextricably linked. The age of the universe is calculated using this same simple logic, but on a cosmic scale. The distance in our analogy is the current scale of the observable universe. The speed is the Hubble constant, and the time is the age of the cosmos since the Big Bang. If we measure a high value for the Hubble constant, meaning space is stretching at a very rapid pace today, it implies that the universe raced to its current enormous size very quickly, which would make it comparatively young. If we measure a lower value for the Hubble constant, indicating a more sedate current expansion, it suggests the universe took a longer, more gradual path to its present state, making it older. This relationship gives the Hubble constant its immense importance. It's not just a speedometer, it's a cosmic clock. This is where the Hubble tension transforms from an abstract disagreement into a direct confrontation with our cosmic history. The two competing values for the Hubble constant don't just disagree on a speed. They tell two different stories about the age of everything. Let's do the math. Using the direct measurement from the cosmic distance ladder, the value of around 73 kilometers per second per megaparsec, the calculated age of the universe comes out to approximately 12.5 billion years. Now, let's use the value inferred from the cosmic microwave background by the Planck satellite, around 67 kilometers per second per megaparsec. This slower expansion rate gives us an age of about 13.8 billion years. That's a difference of over 1 billion years. 1 billion years is an almost unimaginable span of time. It's more than twice the age of our planet Earth. This isn't a minor discrepancy. It's a fundamental conflict over the timeline of existence itself. The plot thickens considerably when we compare these calculated ages with the oldest objects we can actually observe in the cosmos. For instance, astronomers have identified incredibly ancient stars within our own Milky Way galaxy that are found in globular clusters. By analyzing their light, we can determine their composition and, through sophisticated stellar evolution models, estimate their ages. The very oldest of these stars are consistently calculated to be around 13.4 billion years old. This creates a serious problem if the universe itself is only 12.5 billion years old, as the higher Hubble constant suggests. It is an absolute impossibility for stars to be older than the universe they reside in. They simply wouldn't have had the time to form. The existence of these ancient stars acts as a powerful independent check, and they strongly side with the older age proposed by the Planck measurement. This external evidence adds immense weight to the argument that there might be something incomplete in our understanding of the local, direct measurements, making the Hubble tension not just a statistical argument but a tangible paradox that challenges the very chronology of the cosmos. To truly appreciate the depth of the Hubble tension, we need to understand that it's not just a disagreement about a number, it's a fundamental clash between two different ways of seeing the universe. On one side, we have the local measurements, a direct probe of the cosmos as it is today. On the other, the global measurements, which use the early universe as a starting point to predict the present. The fact that these two powerful methods yield different results suggests we might be missing a crucial piece of the cosmological puzzle. The cosmic distance ladder method gives us that higher value, around 73 or 74 kilometers per second per megaparsec, because it's taking a direct snapshot of the current expansion. It's like measuring the speed of cars on a highway today by physically clocking them with a radar gun. This approach relies on a chain of well-understood, nearby object Cepheid variable stars and Type 1, a supernova, to directly gauge distances and velocities of galaxies in our relatively recent cosmic neighborhood. The strength of this method is its directness. It's not based on any grand cosmological model. It simply observes what is happening right now. If this measurement is correct, it implies that the universe is expanding faster today than our best models, which are built on the pristine conditions of the early universe, predict it should be. Conversely, the cosmic microwave background method from the Planck satellite gives us a lower value, around 67 kilometers per second per megaparsec, because it's essentially a prediction. It's not measuring today's expansion directly. Instead, it takes the exquisitely detailed baby picture of the universe provided by the CMB and uses our incredibly successful standard model of cosmology, lambda cold dark matter, to run the cosmic film forward in time. This model, which beautifully explains the large-scale structure of the universe and the distribution of galaxies, predicts what the expansion rate should be now based on the initial conditions and the known ingredients of the cosmos: normal matter, dark matter, and dark energy. The strength of this method is its comprehensiveness. It provides a complete, self-consistent story of cosmic evolution from the first moments to the present day. For these two results to be in conflict, it means that the story our model tells about what happened between that early snapshot and today might be incomplete. This discrepancy is cosmologically significant precisely because the error bars on both measurements have shrunk to the point where they no longer overlap. We are left with a clear, stubborn gap. This makes it highly unlikely that the tension is due to a simple observational error or a mistake in calibration. Astronomers on both sides have spent years searching for such systematic errors. Teams using the Hubble and now the James Webb Space Telescope have painstakingly cross-checked the Cepheid measurements, ruling out many potential sources of error. The Planck team has similarly scrutinized their data for any systematic effects that could skew their results. Neither side has found a convincing error. This points toward a far more exciting possibility: that the lambda CDM model, for all its phenomenal success, is missing something. The leading hypothesis is that this something is a new ingredient or a new property of an existing ingredient in our cosmic recipe. Perhaps dark energy is not a constant cosmological force as Einstein proposed, but is instead dynamic, changing in strength over time. Maybe it grew stronger much more recently than we thought, giving the expansion rate an unexpected boost in the latter half of the universe's history. Another compelling idea is that there exists an entirely new type of dark radiation, often referred to as dark radiation or sterile neutrinos, that flooded the early universe and subtly altered the physics of the Big Bang's afterglow, throwing off the predictions we make from the CMB. There are even more exotic proposals, such as the possibility that dark matter possesses unknown interactive properties, or that Einstein's theory of general relativity itself, the foundation of all modern cosmology, requires modification on the largest possible scales. The Hubble tension is therefore much more than a technical debate. It is a potential window into new physics, a clue that our understanding of the universe, as profound as it is, remains wonderfully incomplete. This persistent and growing gap between our two best ways of measuring cosmic expansion is more than a simple disagreement. It's a profound anomaly that points toward a thrilling and revolutionary possibility. The most exciting interpretation of the Hubble tension is that it's our first real observational hint that our standard model of the universe, for all its incredible predictive power, is incomplete. We might be staring at the edge of known physics, a clue that something is missing from our cosmic recipe book, something that requires a monumental update to our fundamental understanding of reality. Our current standard model, known as lambda cold dark matter or lambda CDM, is arguably one of the greatest achievements in scientific history. It's a remarkably simple yet powerful framework that describes a universe made up of about 5% normal matter, the atoms that make up stars, planets, and us, about 27% cold dark matter, which provides the gravitational scaffolding for galaxies, and about 68% dark energy, represented by the cosmological constant lambda, which drives the accelerated expansion. This model beautifully explains the large-scale structure of the cosmos, the precise patterns in the cosmic microwave background, and the distribution of galaxies we observe. But the Hubble tension is a crack in this elegant facade. It suggests that when we use the early universe to predict the present using lambda CDM, we get a different answer than when we directly measure the present itself. This implies that the model, as it stands, might not be correctly describing the universe's entire evolutionary history. So what could this new physics look like? Cosmologists are exploring a fascinating menu of exotic possibilities, each more mind-bending than the last. One leading idea is that dark energy is not the simple, constant force Einstein imagined. In our standard model, dark energy is represented by the cosmological constant, meaning its energy density remains unchanged as the universe expands. But what if it's dynamic? This idea, often called quintessence, proposes that dark energy is a field that can evolve over time, perhaps growing stronger or weaker. If dark energy was slightly stronger in the last few billion years than our model assumes, it would have given the expansion rate an extra boost, neatly explaining why the universe is expanding faster today than the CMB predicts. It would be as if the cosmic accelerator pedal was pressed down a bit harder than we thought partway through the journey. Another compelling avenue involves the mysterious component known as dark matter. Our model assumes it's cold and non-interacting, meaning dark matter particles mostly just feel gravity and pass through each other and normal matter without a trace. But what if that's not entirely true? Perhaps dark matter has some previously unknown interactive properties. Maybe it can decay into lighter particles or interact with itself or with dark energy in ways we haven't yet imagined. Even a small amount of such interaction could have subtly altered how structures formed in the early universe, changing the sound horizon recorded in the CMB and thus throwing off the prediction for today's expansion rate. It's a reminder that we still have no idea what dark matter actually is, and its true nature could hold the key to this puzzle. There are even more radical proposals on the table. Some physicists are investigating the possibility that we need to add a new, fourth type of neutrino to the particle zoo. The three known neutrinos are ghostly particles that barely interact with matter and were abundant in the early universe. A new, sterile neutrino would have been even less interactive, effectively acting as a form of dark radiation that increases the total radiation content of the young cosmos. This would change how fast the early universe expanded, which in turn changes the size of the ripples we see in the CMB. By adjusting this early expansion history, the model's prediction for the present-day Hubble constant could shift upward, potentially bridging the gap with the direct measurements. Perhaps the most profound possibility of all is that the discrepancy is pointing not to a new particle or field, but to a flaw in our very understanding of gravity itself. Einstein's theory of general relativity has passed every test thrown at it for over a century, but those tests have largely been within our solar system or in strong gravitational fields around black holes. We have never been able to rigorously test it on the largest possible scale, the scale of the entire observable universe. It is entirely possible that general relativity, while stunningly accurate in most regimes, requires modification when applied to the cosmic horizon. If gravity behaves differently on the largest scales, it would completely alter our interpretation of both the cosmic expansion history and the growth of structure, potentially resolving the tension by overhauling the foundational theory upon which all of modern cosmology is built. The Hubble tension, therefore, is not just a problem to be solved. It is a potential beacon guiding us toward the next great revolution in physics, one that could redefine our comprehension of space, time, and the fundamental forces that weave the cosmos together. To understand how the very largest structures in our universe came to be, we must journey back to the very smallest scales imaginable, to a time when the entire cosmos was smaller than a single atom. In that first fleeting moment after the Big Bang, the universe was a seething, dense, and incredibly hot soup of energy and nascent particles. And in this primordial frenzy, empty space was not truly empty. According to the bizarre rules of quantum mechanics, even a perfect vacuum is never completely still. It is a turbulent sea of activity, where pairs of particles and antiparticles constantly flicker into and out of existence for unimaginably short periods of time. These ephemeral appearances are known as quantum fluctuations, and they represent the fundamental uncertainty and energy inherent in reality itself. For the most part, these tiny fluctuations are inconsequential, canceling themselves out almost immediately. But in the infant universe, they were about to be given a role of cosmic importance. This is where the theory of cosmic inflation enters the story. We believe that in the first fraction of a second, the universe underwent a period of hyper-expansion, inflating from a subatomic speck to something roughly the size of a grapefruit in less than a billionth of a billionth of a billionth of a second. This inflationary burst did something extraordinary to those quantum fluctuations. It acted like a cosmic amplifier, stretching those minute, subatomic ripples in the fabric of space-time across the entire universe. The tiny pockets of slightly higher density and the tiny voids of slightly lower density, which once existed only on a quantum scale, were magnified to astronomical proportions. They were frozen into the very geometry of the expanding universe, becoming the first large-scale imperfections in an otherwise smooth and uniform cosmos. These imprinted ripples are the cosmic seeds from which everything we see today would eventually grow. After inflation ended and the universe continued its more sedate expansion, gravity began to work on these seeds. The regions that had been stretched into slight overdensities had a tiny bit more gravitational pull than their surroundings. Over hundreds of millions of years, this extra gravity acted like a magnet, slowly pulling in dark matter and normal matter from the less dense areas around them. This process of gravitational accretion is how the first stars, the first galaxies, and eventually the vast cosmic web of clusters and superclusters formed. The distribution of galaxies we map in the sky today is a direct, blown-up map of those original quantum fluctuations. The pattern is not random. It carries the specific statistical signature of a quantum process that was stretched to cosmic size. This profound link between the quantum world and the cosmic scale is not just a beautiful theory. It is the very reason we can use the cosmic microwave background to measure the universe's expansion. The CMB is that baby picture, and the tiny temperature variations we see in it, those hot and cold spots, are the direct descendants of those inflated quantum fluctuations. They show us the pattern of dense and less dense regions in the plasma of the early universe. By meticulously measuring the statistical properties of this pattern, the preferred sizes and distribution of these spots, cosmologists can deduce fundamental parameters of the cosmos, including its expansion history. The preferred size of these spots, known as the sound horizon, acts as a fixed standard ruler. Measuring its apparent angular size on the sky allows us to calculate the distance to the CMB, which in turn tells us how the universe has expanded from that early moment until now. Therefore, our most precise measurement of the Hubble constant from the Planck satellite is ultimately a measurement rooted in quantum mechanics. It is a calculation that traces a direct line from the unpredictable flicker of virtual particles in the first instant of time to the large-scale structure of the universe we observe today. This incredible connection means that the Hubble tension might not just be a problem with our measurements of expansion, but could potentially point to a misunderstanding of how these quantum fluctuations were imprinted or how they evolved, suggesting that our models of either inflation or very early universe physics might need a subtle but crucial adjustment. But the cosmic microwave background isn't the only place we can find the imprint of those primordial sound waves. Their echo is also frozen into the large-scale structure of the universe we see today, providing a completely independent and powerful way to measure cosmic expansion. This phenomenon is known as Baryon acoustic oscillations, or BAO, and it acts as a giant standard ruler etched across the cosmos. To understand how this works, we need to go back to that hot, dense plasma of the early universe. In the first few 100,000 years, the universe was a seething soup of light and matter, tightly coupled together. Gravity was trying to pull matter into the slight overdensities created by inflation, but the intense pressure of the radiation was pushing back, creating powerful spherical sound waves that rippled outward through the plasma. These were genuine pressure waves, much like the sound waves that traveled through air, compressing and rarefying the matter as they went. The key moment came when the universe cooled enough for atoms to form during what's called recombination. Suddenly, the light could travel freely. That light is the CMB we see today, and the matter was left behind. Without the radiation pressure to push back, the sound waves stopped in their tracks. They froze instantly, leaving behind a very specific signature, spherical shells of matter that had been pushed outward by the waves. Imagine a single pebble dropped into a still pond, creating ripples that expand outward. Now imagine the pond instantly freezing solid, preserving those perfect circular ripples in the ice. That's essentially what happened on a cosmic scale. Each of those original overdensities acted like a pebble, and the sound wave it generated created a spherical shell of matter with a very specific radius. This radius is our cosmic standard ruler. We know its true physical size from the physics of the early universe. It's determined by how far sound could travel in the plasma before the universe cooled. That distance is about 500 million light-years. Now, for the last 13 billion years, the universe has been expanding, and that frozen shell has been expanding with it, being stretched by the growth of space itself. Today, when we look out at the universe and map the positions of millions of galaxies, we can still detect this subtle pattern. By measuring the apparent size of this standard ruler on the sky at different distances, and thus different look-back times, we can measure how the universe has expanded throughout its history. It's a direct geometric measurement, incredibly robust and almost free from the systematic errors that can plague other methods. The results from BAO measurements are particularly fascinating because they don't directly side with either camp in the Hubble tension debate. Instead, they act as a crucial referee. When astronomers use galaxy surveys like the Sloan Digital Sky Survey to measure the BAO scale, they get a value for the expansion rate that beautifully agrees with the prediction from the Planck CMB data. This gives tremendous support to the lambda CDM model and the lower Hubble constant value. The BAO method provides a powerful and independent check that confirms our model of the universe's evolution from its early state is essentially correct. This makes the persistent disagreement from the local distance ladder measurements even more profound and puzzling, because it suggests that the problem isn't with our understanding of the universe's overall history, but perhaps with our measurement of the current local expansion rate itself. The BAO ruler, etched in the very distribution of galaxies, tells us that the cosmic model is sound, forcing us to look for new physics that might only be affecting our local cosmic neighborhood. To understand the full cosmic story, we must account for all the characters on the stage, including the most elusive ones that shaped the universe's fiery youth. In its earliest epochs, the expansion rate wasn't dominated by matter or dark energy, but by radiation. For several 100,000 years, the universe was an opaque, blazingly hot plasma, so dense that light photons could not travel freely. These photons weren't just passive bystanders, they were a dominant form of energy, exerting immense outward pressure that counteracted gravity's inward pull. This radiation pressure was a primary driver of the expansion in this initial phase, causing the young cosmos to expand and cool at a rate dictated by its intense energy density. The influence of this early radiation is permanently imprinted on the cosmos, setting the initial conditions from which everything else evolved. But photons weren't the only relativistic particles flooding the early universe. A far more ghostly population was also present in staggering numbers, neutrinos. For every proton in the universe today, there are roughly 1 billion neutrinos passing through you every second, utterly unnoticed. These tiny, neutral particles barely interact with anything, but in the first second after the Big Bang, they were trapped in the dense soup, flowing like a fluid and contributing significantly to the total energy budget. Their presence, along with photons and other exotic particles, defined the early expansion history. The more relativistic species of particles moving at or near the speed of light there were in this primordial cocktail, the faster the universe expanded during those first critical moments. This is because radiation's energy density dilutes much faster than matter as space expands. As the volume grows, the energy of radiation drops more precipitously. So a universe rich in relativistic particles expands very rapidly at first, but then that expansion rate drops off more quickly as that energy dilutes away. This early radiation-dominated era left behind a crucial fossil that astronomers used to probe the universe's contents, the effective number of neutrino species. Our standard model of particle physics predicts very precisely how many types of neutrinos should have been present: 3, the electron, muon, and tau neutrinos. However, measurements of the cosmic microwave background are so sensitive that they can actually count these relativistic species by detecting their subtle gravitational influence on the plasma oscillations. Intriguingly, some analyses of the CMB data have occasionally hinted at a value slightly higher than 3, suggesting the possible existence of an additional, sterile type of neutrino or another unknown relativistic particle that existed in the early universe. This isn't confirmed, but it's a tantalizing idea because adding just one more lightweight relativistic particle would have increased the early expansion rate. This would, in turn, alter the size of the sound horizon imprinted in the CMB. If the early universe expanded faster than we think, then the sound waves would have had less time to travel, resulting in a slightly smaller standard ruler. This is where these ancient particles connect directly to the modern Hubble tension. A smaller early universe sound horizon would mean that to match the precisely measured angular size of that ruler we see in the CMB today, the universe would have had to expand more in the intervening time. This adjustment would nudge the predicted value for the present-day Hubble constant upward, potentially bridging the gap between the Planck measurement and the higher value from the distance ladder. While the evidence for this extra radiation is not yet definitive, it remains one of the most compelling and well-motivated potential solutions to the crisis, suggesting that the answer to our modern cosmic dilemma might be hidden in the physics of the universe's first second. This cosmic detective story wouldn't be complete without another brilliant and completely independent tool in our arsenal, the phenomenon of gravitational lensing. Predicted by Einstein's theory of general relativity, this effect occurs because massive objects don't just create a gravitational pull, they actually warp the very fabric of space-time around them. Think of it like placing a heavy bowling ball in the center of a stretched-out trampoline. The trampoline fabric dips under the weight. Now, if you roll a marble across that warped surface, its path will curve around the dip. In the cosmos, the bowling ball is a massive object like a galaxy cluster, and the marble is a beam of light from a distant background galaxy. The light doesn't get pulled by gravity in the traditional sense. Instead, it simply follows the curved path of the warped spacetime around the massive cluster. This means the light from the distant galaxy is bent around the foreground cluster, often creating multiple, distorted, or magnified images of that same background galaxy from our viewpoint here on Earth. It's nature's own telescope, and a powerful one at that. But how does this beautiful cosmic illusion help us measure the expansion of the universe? The key lies in a specific and incredibly useful type of lensing called time delay lensing. This occurs when the gravitational lens creates not just one, but multiple distinct images of the same background object, often a flickering quasar. Because each of these light paths snakes around the massive foreground galaxy along a slightly different route, the distances each beam travels are not the same. One path might be slightly longer than another. This means that if the background quasar suddenly flares in brightness, that flash of light won't arrive at Earth at the same time in all the different images. There will be a delay, sometimes days, weeks, or even months between when the flare appears in one image and when it appears in another. This time delay is the crucial measurement. It's like several cars leaving the same starting point at the same time but taking different, winding routes to the same finish line. The difference in their arrival times tells you something about the length and complexity of each path. By meticulously modeling the mass distribution of the foreground galaxy that's acting as the lens figuring out exactly how it warps spacetime, astronomers can calculate the geometric difference in the length of these light paths. They can predict what the time delay should be based on the geometry of the lens. However, the actual observed time delay also depends on another critical factor, the overall scale of the universe, which is governed by the Hubble constant. A universe that is expanding faster has a larger scale, meaning the absolute distances the light has to travel are greater. This stretches the time delay. So, by comparing the predicted geometric delay with the actual observed delay, scientists can essentially reverse engineer the calculation to solve for the Hubble constant. It's a completely independent method that relies on fundamental physics without needing the traditional cosmic distance ladder. Teams like the H0 Lenses in Cosmograil Wellspring or Holy Cow project have used this technique with exquisite precision, analyzing multiple lensed quasars. Their results have been fascinating and deeply significant in the context of the Hubble tension. They have consistently obtained values that intriguingly lie right in between the two competing numbers, often landing around 73.5 kilometers per second per megaparsec. This positioning is more than just a compromise. It's a powerful piece of evidence that suggests the local distance ladder measurements might be closer to the true value, while also providing a crucial cross-check that is free from many of the potential systematic errors that could affect other methods. It's a testament to the creativity of astronomers, using the universe's own distortions as a precision tool to measure its most fundamental property. This profound connection between the present and the ultimate future makes the Hubble constant far more than an abstract measurement. It is the key that unlocks the final chapter of the cosmos. The rate at which space is stretching today, quantified by h0, is the single most critical factor in determining which of several possible destinies awaits our universe. It all comes down to a cosmic tug of war between two opposing forces: the relentless outward push of dark energy, which drives the acceleration, and the inward pull of gravity, exerted by all the matter, both seen and unseen, trying to hold the universe together. If the expansion rate is high enough and dark energy's repulsive force proves to be the dominant and enduring victor in this struggle, the universe is set on a course for what cosmologists call heat death, or the Big Freeze. In this scenario, the acceleration continues unabated forever. Galaxies beyond our local gravitationally bound group will continue to recede until they accelerate beyond our cosmic horizon, their light forever too red-shifted and too faint to ever detect again. The universe will become a vast, ever-cooling emptiness, with isolated islands of galaxies drifting apart in an ever-expanding void until all star formation ceases and the last stars flicker out, leaving behind a cold, dark cosmos of black holes and stellar remnants. However, a different value for the Hubble constant and the properties of dark energy could point toward a far more dramatic ending: the Big Rip. This fate hinges on the possibility that dark energy is not a constant force but something far more exotic and potent, known as phantom energy. If the Hubble constant were part of a model where dark energy's strength actually increases over time, its repulsive power would eventually overcome not just the gravity between galaxies, but every binding force in existence. In this terrifyingly violent finale, first galaxy clusters, then individual galaxies, then solar systems, planets, and even the very atoms that constitute all matter would be torn apart by the uncontrollable expansion of space itself. The universe would meet its end not with a slow fading, but with a catastrophic shredding of the fabric of reality. A third, though now largely disfavored possibility, was the Big Crunch. This was the original expected fate before the discovery of dark energy. If the Hubble constant were much lower and the density of matter in the universe were high enough, gravity would eventually win the long-term battle. The expansion would slow, halt, and then reverse, pulling all matter and energy back together in a fiery collapse that mirrors the Big Bang in reverse, culminating in a singular state of incredible density and heat. While current measurements of the acceleration have effectively ruled out this cyclical ending, it remains a powerful reminder of how delicately our cosmic fate is balanced on the precise value of a few fundamental parameters. Ultimately, the Hubble constant is the linchpin in these grand cosmic forecasts. Its value, combined with our measurements of the universe's density and the nature of dark energy, writes the final sentence in the story of everything. By refining our measurement of this number and understanding the tension between different results, we are not just solving an academic puzzle, we are reading our own ultimate destiny written in the expanding fabric of space itself. There's another remarkable way we can witness the expansion of the universe, one that doesn't just rely on measuring distance and velocity, but actually observes the direct relativistic effect of stretched time itself. This method involves studying the light curves of distant Type 1a supernova, but with a focus on a subtle yet profound detail. These cosmic explosions appear to unfold in slow motion the farther away they are. This isn't an illusion or a measurement error. It's a direct consequence of the expansion of space and a powerful confirmation of our cosmological models. When we look at a supernova that is billions of light years away, we are not just looking across space, we are peering back into time. The light from that explosion has been traveling for eons to reach us, and during its long journey, the very fabric of the universe has been stretching. This expansion does something incredible to the light wave. It stretches it out, shifting its color to the red and, crucially, stretching out the duration of the signal we receive. Imagine a clock ticking in that distant galaxy. Each tick represents a pulse of light. As the light from each tick travels through the expanding universe, the space between those wavefronts gets stretched. By the time the light from the first tick and the light from the second tick reach our telescopes, more time has elapsed between them than actually passed on the clock in the host galaxy. The entire event, the brightening and the fading of the supernova, appears to us as if it's happening in slow motion. This stretching of time is precisely predicted by our theory of an expanding universe. The factor by which the light curve is time dilated should be exactly equal to a quantity known as 1 plus the redshift, or 1 plus z. For a supernova at a redshift of 1, meaning the universe has stretched by a factor of 2 since the light left the star, the event should appear to unfold exactly twice as slowly as an identical supernova happening nearby. This provides a completely independent test. We can measure the redshift of the host galaxy spectroscopically, which gives us the factor 1 plus z. Then we can carefully measure the actual duration of the supernova's light curve, how long it takes to reach peak brightness and then fade away, and compare it to the well-calibrated template of a local supernova. The two numbers should match perfectly if the universe is truly expanding, and they do. This observed time dilation is a direct observational signature that the expansion is real. It rules out alternative explanations for the redshift that don't involve expanding space, such as the idea that light simply gets tired and loses energy over long distances. If that were the case, the light would be redshifted, but the duration of the event would appear normal to us. The light curve would not be stretched. The fact that we clearly see this time dilation effect is a beautiful and robust validation that the redshift is indeed a measure of the expansion of space itself. But this phenomenon is more than just a confirmation. It's a powerful tool for measuring how the expansion rate has changed over billions of years. By studying the light curves of supernova at many different redshifts, we can effectively map out the history of the universe's expansion. We can see how the time dilation factor changes with distance, which tells us how the stretch of space has accumulated over time. This data provides crucial, direct evidence for the epoch when the expansion transitioned from deceleration to acceleration. The light curves of the most distant supernovas show a time dilation factor that is consistent with a universe that was expanding more slowly in the past, which is exactly what we expect if dark energy has recently begun to dominate and speed things up. This slow-motion view of the most ancient stellar deaths provides a unique and compelling clock, one that ticks in sync with the expansion of the cosmos, allowing us to read the history of the universe's growth directly from the stretched-out light of its most violent explosions. To truly grasp how the universe expands at the most fundamental level, we must move beyond analogies and into the mathematics that actually describe reality. This brings us to the heart of Einstein's theory of general relativity, which provides the profound and precise framework for understanding the metric expansion of space. The key idea is that gravity is not a force in the traditional sense, but rather a curvature of spacetime itself. Massive objects like stars and planets warp the four-dimensional fabric of the cosmos, and this curvature tells other objects how to move. When we apply this revolutionary concept to the entire universe, a universe that is, on the largest scales, homogeneous and isotropic, meaning it looks the same in every direction and from every point, we arrive at a set of equations that govern the evolution of everything. These are the Friedmann equations, named after the Russian physicist Alexander Friedmann, who derived them from Einstein's field equations in 1922. They are the master equations of cosmology, and they directly tie the expansion rate of the universe to its fundamental contents. The first Friedmann equation is, in essence, a cosmic energy balance sheet. It relates the square of the Hubble parameter, which measures the expansion rate at any given time, to three key components: the total energy density of the universe, its spatial curvature, and the cosmological constant. It tells us that the kinetic energy of the expansion is balanced by the gravitational potential energy of everything contained within the universe. The second equation describes how the expansion accelerates or decelerates based on the pressure and density of its contents. What makes these equations so powerful is how they connect the grand motion of the cosmos to the stuff within it. The energy density term isn't a single thing, it's a sum of all different types of energy. This includes the density of normal matter, like atoms and molecules, which has gravity but exerts negligible pressure. It includes radiation, like photons, which have both energy density and significant pressure. And it includes dark matter and dark energy, the mysterious components that dominate the universe's budget. The equations show us that different types of energy affect the expansion in dramatically different ways. Matter and radiation slow the expansion down because their gravity pulls everything together. A positive cosmological constant, representing dark energy, has a negative pressure and acts to speed the expansion up, acting as a kind of repulsive gravity. The curvature term in the equations is equally profound. It tells us about the overall geometry of the universe. If the density of the universe is exactly equal to a critical value, space is flat, like an infinite sheet of paper. If the density is higher, space is positively curved, like the surface of a sphere, and the universe is closed and finite. If the density is lower, space is negatively curved, like a saddle, and the universe is open and infinite. Observations of the cosmic microwave background have told us with incredible precision that we live in a universe that is very nearly, if not exactly, flat. This means the curvature term in the Friedmann equations is essentially zero, simplifying our cosmic accounting and telling us that the energy density of the universe is at that critical value. Solving these equations under different assumptions allows cosmologists to model the entire history of the universe, from a fraction of a second after the Big Bang to the distant future. They are the engine behind the lambda-CDM model, enabling us to run the cosmic film forward and predict what the Hubble constant should be today based on the conditions of the early universe. The fact that this prediction now clashes with direct measurements is not a failure of the equations themselves, but a powerful indication that the ingredients we are plugging into them, our understanding of dark energy, dark matter, or perhaps the very nature of gravity, might be incomplete. The Friedmann equations are the immutable rules of the game. The Hubble tension suggests we may still be learning the identities of all the players. This brings us to one of the most persistent and understandable misconceptions about the expanding universe, the nature of the redshift itself. It's incredibly natural to hear that galaxies are moving away from us and picture them rocketing through a static, empty void. Their light waves stretched like the sound waves from a receding siren, a phenomenon known as the Doppler effect. While this is a useful analogy for understanding the basic idea of wavelength stretching, it is fundamentally incorrect when applied to the large-scale expansion of the cosmos. The redshift we measure from distant galaxies is not a Doppler shift in the traditional sense. It is something far stranger and more profound, a cosmological redshift, and the difference between these two concepts is absolutely crucial. A true Doppler shift occurs when an object is moving through a fixed, unchanging medium. The classic example is the ambulance siren. As the ambulance moves toward you, the sound waves are compressed, raising the pitch. As it moves away, the waves are stretched, lowering the pitch. The key point is that the motion is through space. The space between you and the ambulance isn't changing. The ambulance itself is doing the moving. If we applied this directly to galaxies, it would imply they are all flying away from us through a stationary arena of space, which would indeed suggest we are at the center of some grand cosmic explosion. But that's not what's happening. Cosmological redshift is a direct and inevitable consequence of the expansion of space itself during the light's multi-billion-year journey. Imagine a photon, a particle of light being emitted by a distant galaxy. At the moment of its emission, it has a very specific wavelength. It then begins its epic voyage across the universe toward our telescopes. But the universe is not static during this journey. The very fabric of space through which this photon is traveling is continuously stretching. As space expands, it stretches the photon's wavelength along with it. By the time this weary traveler finally arrives at our detectors, its wavelength has been systematically lengthened or redshifted by the cumulative expansion that occurred all along its path. The photon isn't tired. It hasn't lost energy to some cosmic friction. The energy loss is a direct result of the stretching of its wave. The longer the journey, the more time for space to expand, the greater the redshift we observe. This is why redshift, denoted as Z, is such a powerful proxy for both distance and look-back time in cosmology. This distinction resolves the puzzling idea that we might be at the center of the universe. In the Doppler interpretation, everything flying away from us specifically would indeed put us in a privileged position. But in the cosmological redshift interpretation, the view is the same from every galaxy. An observer in that distant galaxy we're watching would see our Milky Way redshifted by exactly the same amount. From their perspective, the space between us has expanded, stretching the light from our galaxy and shifting it to the red. There is no center to the expansion because the expansion is a property of space itself, not motion through it. This subtle but monumental difference is what transforms our understanding from a simple model of flying objects to the mind-bending reality of a dynamically evolving space-time, a universe whose very geometry is writing its history into the light that passes through it. While the universe as a whole is engaged in the smooth, relentless expansion known as the Hubble flow, the reality for any individual galaxy is far more chaotic. Imagine a vast, steadily flowing river. This is the Hubble expansion, carrying everything along with it. Now, picture leaves and twigs on that river's surface, each one also darting and spinning in small, frantic circles due to local eddies and currents. Those random, local motions are the peculiar velocities of galaxies, and they are absolutely crucial to account for if we want to measure the true, underlying current of the river itself. Peculiar velocities are the real, physical motions of galaxies through space, as opposed to the apparent motion caused by the stretching of space between them. They are caused by the irresistible tug of gravity from nearby massive structures. Our own Milky Way, for example, is not simply drifting peacefully with the Hubble flow. We are being pulled at a staggering 600,000 kilometers per hour toward the Great Attractor, a massive concentration of galaxies in the direction of the Centaurus constellation. Similarly, the entire Andromeda galaxy is not just receding from us due to expansion. It is actually moving toward us through space at about 110 kilometers per second, destined to collide with the Milky Way in billions of years because their mutual gravitational attraction overwhelms the expansion of the universe on such a local scale. These are not small corrections, they are massive deviations that, if ignored, would completely obscure our view of the cosmic expansion. This is why measuring the true Hubble constant is such a painstaking process of subtraction. Astronomers must first meticulously measure a galaxy's observed redshift, which is a combination of the cosmological redshift from the Hubble flow and the Doppler shift from its peculiar velocity. They then have to calculate and remove the estimated peculiar velocity component to isolate the pure Hubble flow signal. To do this, they construct elaborate models of the cosmic web's mass distribution, mapping the gravitational pull of nearby galaxy clusters and vast cosmic voids. These models predict how much a galaxy should be tugged from side to side by its local gravitational environment. It's a cosmic balancing act, and any errors in these models directly translate into errors in the final calculation of the expansion rate. Some scientists have even proposed that our local galactic neighborhood might be inside a particularly large cosmic void, which would mean our peculiar motion is greater than previously thought, potentially explaining a part of the Hubble tension by suggesting our local measurement of expansion is slightly off. This intricate dance of separating the universal motion from the local chaos is a fundamental and ongoing challenge in our quest to pinpoint the universe's true expansion speed. This accelerating expansion doesn't just dictate the future fate of the cosmos. It actively shapes what we are able to see right now, defining the ultimate boundaries of our observable universe. We often picture the observable universe as a vast sphere centered on Earth, containing every single object whose light has had time to reach us since the Big Bang. But this cosmic horizon isn't a fixed, static boundary like the edge of a map. It's a dynamic, evolving limit, and its size and composition are dictated directly by the expansion history of the universe. The key factor is a simple but profound race, the race between the speed of light and the stretching of space. For a distant galaxy to be visible to us, the light it emits must be able to outrun the expansion of the space between us during its entire multi-billion-year journey. If the space between us and that galaxy is stretching too quickly, the light will never make any progress toward us, effectively running on a cosmic treadmill it can never win. This creates a fundamental limit known as the cosmological horizon. There are regions of the universe so far away that the space between us and them is expanding faster than the speed of light. This might sound like a violation of physics, since nothing can travel through space faster than light. However, there is no limit on how fast space itself can expand. The light from those ultra-distant regions is still being emitted, but it is traveling through space that is stretching so rapidly that the total distance the light needs to cover is actually increasing faster than the light can move. As a result, that light will never ever reach us. Those galaxies are forever beyond our observational reach, hidden behind a horizon that is not made of matter or energy, but of geometry and kinematics. The current expansion rate, the Hubble constant, is the engine that controls this process. A higher expansion rate means this horizon is closer to us. It means a greater fraction of the universe is already forever lost to our view, receding into unreachability at this very moment. This leads to a deeply counterintuitive reality about our cosmos. The observable universe is not the entire universe. In fact, it is almost certainly an infinitesimally small fraction of it. The full universe is likely vastly larger, perhaps even infinite, but we are causally disconnected from most of it. We are like a sailor on a vast, foggy ocean, able to see only a small circle around our ship, unaware of the distant shores or other ships that lie beyond the impenetrable mist. The size of that visible circle is determined by the expansion rate of the universe. Furthermore, this horizon is not the same for every observer. A hypothetical astronomer in a galaxy a billion light-years away has their own different observable universe. Their cosmic horizon encompasses galaxies that are forever hidden from us, and vice versa. We all live in our own island of visibility, adrift in a much grander cosmos that we can infer but will never directly witness. This means the expansion rate doesn't just change our past and our future. It actively limits our present, defining the ultimate cage for our curiosity, and forever determining which of the universe's secrets we will be allowed to uncover. This brings us to one of the most mind-bending consequences of cosmic expansion, a fact that seems to outright defy the most famous rule in physics but actually reinforces its genius. It is a complete and utter misconception that nothing can travel faster than light. Einstein's theory of special relativity is unequivocal on this point. No object or information can ever be sent through space at a velocity greater than the speed of light. This cosmic speed limit is foundational to our understanding of reality. However, the expansion of the universe operates under a different set of rules entirely, governed by general relativity. The key distinction, once again, is the difference between motion through space and the expansion of space itself. Special relativity sets the speed limit for any journey within the universe. But it places no constraint whatsoever on how fast the universe's very stage, the fabric of space-time, can itself stretch and grow. To grasp how this works, imagine you are an ant standing on the surface of a perfectly elastic rubber band that is 1 meter long. You decide to walk along it at a steady pace of 1 centimeter per second. Special relativity says you, the ant, cannot ever walk faster than your 1 centimeter per second. Now imagine someone begins stretching that rubber band. The space of your one-dimensional world is expanding. Even if you stand completely still, the distance between you and a point on the far end of the rubber band is increasing. The rubber band itself is doing the moving, not you. If the stretching is slow, you could still potentially walk to the other end. But if the stretching is rapid enough, the total length of the rubber band could be increasing by more than 1 centimeter every second. In that case, even if you walked at your maximum speed toward the other end, you would never reach it because the distance you need to cover is growing faster than you can close the gap. The far end of the rubber band is, from your perspective, receding from you faster than your top walking speed. This is precisely what is happening on a cosmic scale. Galaxies embedded in the expanding fabric of space are like ants glued to specific points on that stretching rubber band. They are not propelling themselves through space, they are largely stationary within their local region. But the space between them is growing. For galaxies that are sufficiently close to us, the expansion is relatively slow. The space between us might be growing at a rate of a few dozen or a few hundred kilometers per second, which is well below the speed of light. We can still see these galaxies because their light, moving through that expanding space at light speed, can still make progress toward us and eventually arrive. However, for galaxies that are extremely far away, the cumulative expansion across the vast gulf between us is immense. The total amount of space stretching over that enormous distance can easily add up to a recession velocity that exceeds the speed of light. The light from such a galaxy, like our ant walking on the hyper-stretched rubber band, is fighting a losing battle. It is racing toward us at the ultimate speed, but the finish line is being moved away from it even faster. This establishes a fundamental horizon for our observable universe. There is a critical distance beyond which the expansion of space carries galaxies away from us faster than light can travel. Any light those galaxies emit after crossing that threshold will never reach us. It is not that the light slows down or stops, it continues moving through space at its constant speed. But the space it must traverse is stretching so rapidly that the total distance to us is increasing faster than the light can cover it. This light is forever in transit, destined to never complete its journey. This is why we can only ever see a finite portion of the entire cosmos, a bubble centered on us called the observable universe. The size of this bubble is determined by the expansion rate. A faster expansion means a smaller observable universe as the light speed horizon is closer to us. This incredible reality means that the universe is not just big. Much of it is fundamentally and permanently hidden from our view, not by distance, but by the relentless and accelerating stretching of the very fabric of reality. While our gaze is often fixed on the vastness of the cosmos to understand its expansion, some of the most stringent tests of our cosmological models come from the opposite extreme, the incredibly controlled, precise environment of particle physics laboratories here on Earth. This might seem counterintuitive. How can experiments in underground colliders and atomic traps, which study the behavior of subatomic particles, possibly tell us about the history of the entire universe? The connection is profound and lies in the fact that the laws of physics are universal and unchanging. The same fundamental constants that govern the interactions of quarks and electrons in a lab today also dictated the nuclear reactions that forged the first elements minutes after the Big Bang. By measuring these constants with exquisite precision, we can effectively test the engine that drives our models of cosmic evolution. The most powerful example of this is the study of the primordial elements created during Big Bang nucleosynthesis, or BBN. In the first 3 minutes of the universe's existence, when it was a seething hot plasma of protons and neutrons, the conditions were just right for nuclear fusion to occur on a cosmic scale. This brief period synthesized the lightest elements, most of the helium-4 and deuterium in the universe, along with small amounts of helium-3 and lithium-7. The amounts of these elements produced were exquisitely sensitive to the conditions of the early universe, particularly its expansion rate and density. The faster the universe was expanding during those first few minutes, the less time protons and neutrons had to find each other and fuse, leaving more leftover hydrogen and less helium. The density of normal matter directly influenced how many deuterium nuclei could form before being torn apart again. This is where the particle physics lab becomes our time machine. To calculate the predicted abundances from BBN, cosmologists need to know the precise rates of the nuclear reactions involved. For instance, how likely a proton and a neutron are to fuse into a deuterium nucleus. These reaction rates depend on fundamental constants of nature, like the strength of the strong nuclear force. By meticulously measuring these constants and cross-sections in particle accelerators today, physicists can pin down the physics of BBN with incredible accuracy. They can then run the model and get a very precise prediction for how much deuterium and helium should exist in the universe today. Astronomers then go out and measure the actual abundances of these elements in pristine clouds of gas in distant galaxies or in the atmospheres of very old stars, which act as cosmic fossils preserving the composition of the early universe. The breathtaking result is that these predictions and observations match to within a percent or two. This agreement is a monumental triumph for the Big Bang model. But more than that, it places a powerful constraint on the expansion history of the universe. Any proposed modification to cosmology that would alter the early expansion rate, such as adding new types of relativistic particles or changing the strength of gravity, must not spoil this near-perfect agreement. For instance, a model that proposes a much higher expansion rate in the first few minutes to solve the Hubble tension would overproduce deuterium, creating a clear conflict with observations. The primordial element abundances act as a cosmic speed bump, preventing our theories from veering too far from reality and providing a completely independent, non-cosmological check on the universe's early expansion rate, all verified by painstaking laboratory work on Earth. The unresolved Hubble tension is far more than a debate over numbers. It strikes directly at the heart of our understanding of the universe's most dominant yet mysterious component, dark energy. The core assumption in our standard cosmological model is that dark energy is perfectly described by Einstein's cosmological constant, a form of energy inherent to the fabric of space itself that maintains a perfectly uniform density, never changing as the universe expands. This simple, elegant idea has been the foundation for predicting the universe's evolution from its early state to the present day. However, the persistent discrepancy between the early and late universe measurements of expansion is now forcing cosmologists to confront a radical possibility. What if dark energy isn't constant at all? This is where the Hubble tension transforms from a technical puzzle into a potential revolution. The direct, local measurements from supernova and Cepheids suggest the universe is expanding faster today than our models, built on a constant dark energy, predict it should be. One of the most compelling explanations for this unexpected speed-up is that dark energy's influence has been growing stronger over the last several billion years. Instead of a steady, gentle pressure, it might be a dynamic force that has evolved over cosmic time, a concept physicists call quintessence. This isn't a new particle in the traditional sense, but rather a dynamical field that permeates all of space, one whose energy density could change, potentially increasing and giving the expansion rate an extra, recent boost that our current models didn't account for. The implications of this are staggering. If dark energy is dynamic, it means the acceleration of the universe might not be a permanent, fixed feature. It could be a phase, an era in cosmic history that could potentially weaken or even reverse in the far, far future. This dynamism would completely reshape our predictions for the ultimate fate of everything. The steady, cold future of a big freeze would be replaced by a host of other possibilities, perhaps even a cyclical universe. Furthermore, a dynamic dark energy would imply a rich, new physics beyond the standard model, possibly connecting to other great mysteries like the nature of the quantum vacuum or even string theory. The Hubble tension, therefore, is acting like a compass needle, twitching away from the simple cosmological constant and pointing toward a far more complex and fascinating dark sector, suggesting that the force dominating the cosmos is not a silent, steady background but an active, evolving participant in the cosmic story. While the Hubble tension presents a formidable challenge, the story is far from over. The scientific community is responding not with frustration, but with a new generation of breathtakingly powerful observatories, engineered specifically to chase down this mystery with unprecedented precision. We are on the cusp of a new golden age of observational cosmology, where instruments like the James Webb Space Telescope, the upcoming Nancy Grace Roman Space Telescope, and ground-based behemoths like the Extremely Large Telescope will turn their immense focus toward this single defining problem. Their mission is to systematically eliminate every possible source of error, to measure the cosmos with a clarity we've never before possessed, and to finally determine whether this tension is a flaw in our measurements or a flaw in our fundamental physics. The James Webb Space Telescope, or JWST, is already revolutionizing this pursuit. While Hubble provided the data that cemented the tension, JWST acts as the ultimate cross-examiner. Its primary weapon is its extraordinary infrared sensitivity and razor-sharp resolution. For the cosmic distance ladder, this is a game-changer. JWST can peer through the obscuring dust that often clouds galaxies, allowing it to identify and study Cepheid variable stars and Type Ia supernova in galaxies that were previously too dusty or too distant for Hubble to analyze clearly. Most importantly, JWST is observing the same galaxies Hubble studied. By measuring the same Cepheids with a different, more powerful instrument that is immune to many of the potential systematic errors that could affect Hubble, like the crowding of stars in dense galactic centers or subtle calibration issues, astronomers can perform a definitive check. The early results are in, and they are stunningly consistent with Hubble's earlier measurements. JWST has effectively confirmed that the local measurements are not wrong due to instrumental error. The higher expansion rate persists even with this new, superior eye on the sky. This doesn't solve the tension, but it dramatically narrows the field of possible explanations, forcefully pushing us toward the need for new physics. But JWST is just the beginning. The Nancy Grace Roman Space Telescope, scheduled to launch later this decade, will attack the problem from a different angle: vast panoramic surveys. Where JWST is a powerful zoom lens, Roman will be an immensely wide-angle one. Its core mission involves a gigantic survey of the sky, during which it is expected to discover thousands of new Type Ia supernova. This enormous statistical sample will allow astronomers to construct the cosmic distance ladder with a level of precision that is simply impossible with the relatively small number of supernova we have today. It will map the expansion history of the universe with such fine detail that it can probe the very nature of dark energy itself, testing whether its strength has changed over time. By providing an overwhelming flood of pristine data, Roman will either reveal a subtle systematic error hiding in the small number statistics, or it will put the final nail in the coffin of the standard model, providing irrefutable evidence that the Hubble tension is real and requires a revolutionary explanation. On the ground, a colossal new eye is preparing to open. The Extremely Large Telescope, or ELT, being built in the high desert of Chile, will feature a mirror a staggering 39 meters across. This immense light-gathering power will allow it to perform a crucial task that is difficult for space-based telescopes: obtaining incredibly high-resolution spectra of distant objects. The ALT will be able to measure the redshifts of galaxies with phenomenal accuracy, and more importantly, it will study the peculiar velocities of galaxies with a precision that was previously unthinkable. This will allow cosmologists to build exquisitely detailed maps of the local cosmic flow, subtracting out the random motions of galaxies caused by the gravitational tug of nearby clusters, and voids to isolate the pure Hubble flow expansion with minimal contamination. By cleaning up the data on the local universe's motion, the ALT will ensure that the local measurement of the Hubble constant is as pristine and accurate as physically possible. Together, this trio of observatories represents a coordinated assault on the greatest problem in cosmology. JWST is the precision validator confirming the existing local measurements. The Roman telescope is the statistician providing an enormous definitive dataset to rule out random chance. The ELT is the fine-tuner cleaning up the local data and providing independent checks. Within the next decade, the combined power of these instruments will shrink the error bars on both sides of the tension to such a degree that the disagreement will become impossible to ignore. Either the bars will finally overlap, revealing a subtle error we can now correct, or they will remain stubbornly separate, leaving no doubt that we are witnessing the breakdown of our current understanding of the universe. This isn't a waiting game, it's an active, thrilling investigation, and the next chapter of this cosmic mystery is being written right now by the most advanced machines humanity has ever built. This brings us to a fact that often causes more head-scratching than any other in cosmology: the sheer, mind-boggling size of our observable universe. We are told the universe is 13.8 billion years old, and we know that nothing can travel faster than light. It seems logical, then, to assume that the most distant object we could possibly see is 13.8 billion light-years away. The reality is so much grander and more counterintuitive. The actual radius of our observable universe is not 13.8 billion light-years. It is a staggering 46.5 billion light-years in every direction. How can we see light from an object that is now so far away, if the light hasn't had time to travel more than 13.8 billion years to reach us? The answer, once again, lies in the expansion of space itself, and it perfectly illustrates why the Hubble constant is the key to mapping our cosmic horizon. Imagine a photon of light being emitted from a distant galaxy 13 billion years ago when the universe was in its infancy. At that very moment, that galaxy might have been, say, only a few million light-years away from our location, the spot that would one day become the Milky Way. That photon begins its journey toward us, moving at light speed, but as it travels, the very fabric of space it is moving through is stretching. It's like a runner on a racetrack where the finish line is not only moving away, but the track itself is getting longer with every stride. The photon is making progress, but the total distance it must cover is increasing due to the expansion happening all along its path. By the time that photon finally arrives at our telescopes today, the galaxy that emitted it has been carried away by the expansion of space to a distance that is now 46.5 billion light-years from us. The light tells us where the galaxy was, not where it is. The journey took 13 billion years, but the destination is now vastly farther away than it was at the start of the trip. This is why the current expansion rate, the Hubble constant, is so critical to this calculation. The size of our observable universe is not simply the speed of light multiplied by the age of the universe. It is the speed of light multiplied by the age of the universe, and then factored with the entire history of how space has expanded during that time. The precise value of 46.5 billion light-years comes from solving the equations that describe how a photon's path is integrated over 14 billion years of cosmic expansion. It depends on the amounts of dark energy and dark matter, and it is exquisitely sensitive to the present-day expansion rate measured by h0. If the Hubble constant were significantly higher, it would mean space has been expanding faster, which would place that cosmic horizon. the point of no return where recession velocity equals light speed, much closer to us. Our observable universe would be smaller. If the Hubble constant were lower, the horizon would be farther out. The 46.5 billion light-year figure is a direct consequence of our best measurements of the universe's contents and its current expansion speed. This immense scale has a profound implication. We are forever surrounded by a horizon of unknowability. There are galaxies whose light is only now, after 13.8 billion years, finally reaching us for the first time. But there are also galaxies so far away that the space between us and them is expanding faster than the speed of light. Any light they emit now will be forever stranded, unable to ever make headway against the rushing expansion of space. They are already beyond our cosmic event horizon. We are, each of us, at the center of our own observable sphere, a sphere whose size is dynamically set by the expansion rate of the universe. This means the Hubble tension is not just an academic debate about a number. It is a debate about the actual size of our cosmic home and a fundamental limit on what we can ever hope to know about the totality of existence. And so we find ourselves at a remarkable crossroads in cosmic history, living in what might just be the perfect moment to unravel the mystery of the expanding universe. It's a golden age for cosmology, a brief and privileged window of time that may not last forever, and it's defined by a delicate balance between what we can still see and what we are only just beginning to understand. This era is special for a profound reason. Dark energy, the mysterious force accelerating the expansion, has only recently become the dominant influence in the cosmos. For the first 9 billion years of the universe's existence, gravity was in charge. The collective pull of matter and dark matter was steadily slowing down the expansion, acting as a cosmic brake on the initial impulse of the Big Bang. But around 5 billion years ago, the scales finally tipped. The universe had expanded so much that the density of matter diluted away, while the density of dark energy tied to space itself remained constant. As dark energy took over, the expansion began to accelerate, and the universe entered its current runaway phase. This timing is incredibly fortunate for us as observers. Because this transition happened relatively recently in cosmic terms, we still have a clear and detectable view of both regimes. We can look out into space and back in time to observe supernova from an era when the universe was still decelerating, and we can compare them to more recent explosions that show the clear signature of acceleration. This allows us to directly measure the change in the expansion rate and piece together the entire history of the universe's growth. If we had emerged as a curious civilization just a few billion years earlier, the effect of dark energy would have been too subtle to detect against the overwhelming gravitational pull of matter. The universe would have appeared to be simply slowing down, and we might never have discovered the accelerating expansion at all. Conversely, if we appeared trillions of years in the future, the evidence for this crucial transitional era might be lost forever. This brings us to the precarious nature of our cosmic window. The same acceleration that makes dark energy detectable is also, slowly but surely, closing our blinds on the distant universe. As the expansion accelerates, galaxies beyond our local gravitationally bound group are being pushed away from us at ever-increasing speeds. Eventually, they will be carried so far so fast that their light will no longer be able to overcome the expansion of space to reach us. They will fade from view one by one, crossing what's known as the cosmological horizon. Future astronomers, if any exist, will look out into a much emptier sky. Their observable universe will be limited to the few dozen galaxies of our local group, all bound together by gravity and destined to eventually merge into one giant galaxy. They will have no evidence of the Big Bang, no cosmic microwave background, and no distant galaxies to show them that the universe is expanding. The key clues we now take for granted will be permanently hidden from view. That's why now is such a uniquely privileged moment. We are living in the sweet spot, late enough in cosmic history that dark energy has revealed itself through its dramatic effect on the expansion, but early enough that we still have a vast, observable universe filled with evidence of its past. We can still see the afterglow of the Big Bang. We can still trace the cosmic web of galaxies stretching back billions of years. We have the technological prowess to build space telescopes like Hubble and Webb to measure this expansion with stunning precision, and we have the intellectual curiosity to recognize the profound puzzle it presents. We are witnessing the universe at a time of great change, a pivotal chapter in its story, and we have the front row seats and the tools necessary to read it. This isn't just a happy accident, it's a calling. It means the responsibility to understand the cosmos falls on us, now, in this brief window of opportunity, before the evidence recedes over the horizon and the universe keeps its final secrets forever. From the initial, groundbreaking discovery by Edwin Hubble that the universe is not static but dynamically expanding, to the shocking revelation that this expansion is accelerating due to a mysterious force we call dark energy, our journey through these 30 facts reveals a cosmos far stranger and more magnificent than we ever imagined. We've seen how this fundamental rate of growth, the Hubble constant, is not just a number but a cosmic clock and a measuring tape, allowing us to calculate the universe's age at 13.8 billion years and map the observable cosmos to a radius of 46.5 billion light-years. We've explored the two powerful yet conflicting methods of measurement, the cosmic distance ladder built from Cepheid variables and supernova, and the pristine snapshot of the infant universe from the cosmic microwave background, and the profound crisis their disagreement creates, the Hubble tension, which points toward potential new physics beyond our current understanding. This story connects the quantum flicker of virtual particles in the first instant of time to the vast cosmic web of galaxies we see today, showing how the primordial seeds of structure were stretched by inflation and sculpted by gravity. We've grappled with the reality that the Hubble constant is not truly constant, but has changed over cosmic history in a grand tug of war between the gravitational pull of matter and the repulsive push of dark energy, a struggle that dictates our ultimate fate, from a cold big freeze to a catastrophic big rip. We've cleared up the crucial misconception that galactic redshift is a Doppler effect, explaining instead that it is the stretching of light itself by the expansion of space during its billion-year journey. We've seen how this expansion sets a hard limit on our knowledge, creating a cosmological horizon that forever hides most of the universe from our view. And we've discovered how our local motion, hurtling through space at hundreds of thousands of kilometers per hour, must be carefully subtracted to reveal the true, underlying Hubble flow. This is more than a collection of fascinating facts. It is a single, continuous narrative about our place in the cosmos. The effort to measure the expansion rate ties directly into the universe's origin in the Big Bang, its evolution through the formation of stars and galaxies, and its ultimate fate billions of years from now. It connects the largest scales of the cosmic web to the smallest scales of particle physics labs, where measurements of nuclear reactions verify the story of the universe's first few minutes. And most importantly, we are living in a uniquely privileged moment to witness this story unfold. We emerged at a time when the evidence for acceleration is still detectable, and we possess the technology, with telescopes like Hubble, Webb, Roman, and the ELT, to measure it with breathtaking precision. We are living through a revolution in cosmology, a golden age where the next major discovery about the nature of dark energy, the validity of gravity, or the existence of new particles could be just one observation away. So the next time you look up at the night sky, remember that you're not just looking at a static canopy of stars. You are witnessing a dynamic, evolving, and accelerating universe, and you are here at the perfect time to appreciate the profound and humbling journey of discovery that is forever rewriting our cosmic story. Which of these 30 facts left you the most astonished? Was it the realization that the universe isn't just expanding, but but that its acceleration could one day tear apart the very fabric of reality. Or perhaps it was the humbling truth that most of the cosmos is already forever hidden from our view, receding behind a horizon set by the speed of light itself. Let us know in the comments below. We read every single one and love hearing which cosmic truth resonates with you the most. If this journey through space and time sparked your curiosity, be sure to subscribe and hit the bell so you don't miss our next exploration into the deepest mysteries of the universe. As we bring this investigation to a close, take a moment to reflect on the sheer scale of this human achievement. We are fragile, temporary beings on a small rock orbiting an average star, and yet, through ingenuity and persistence, we have managed to not only deduce that the entire cosmos is expanding, but to actually measure the rate at which it's happening. We've built telescopes that act as time machines, designed spacecraft that map the afterglow of creation, and crafted equations that describe the history and fate of everything. The Hubble tension isn't a sign of failure, it is a testament to our incredible success. It shows that we have peered so deeply into the nature of reality that we are now brushing up against the edges of our own understanding, staring at the first hints of a deeper truth waiting to be uncovered. This pursuit, this endless quest to measure the immeasurable, is one of the most profound and beautiful expressions of what it means to